All right, so now we're going to go over rounding, and when you're rounding with sig figs, there's a few things to think about. Most of the rounding rules follow what you're used to, but there's a few times where you round in kind of a different way. So I'm going to take you through a few sample problems here, and we'll see how it goes. Just for making it a little bit easier, these are all going to be rounded to 3 significant figures. So let's look at the first example. The first example, we have one, two, three, 4 sig figs. So we couldn't leave this number this way because the direction tells us to round it to 3. So we count from left to right, and we find the third sig fig. 1, 2, 3. So number 3 is the third sig fig. We look to the right of that number. If the number that is there is less than 5, then the 3 remains a 3, and we drop the 2, and we end up with 2.53. So that's our answer rounded to 3 sig figs. In the second one, we see 2.536. So again, we're going to round it to 3 sig figs. We count 1, 2, 3. Kind of underline that 3. Next to that 3 is a 6. If the number past the digit that you're rounding is greater than 5, then you round that last digit up. So 2.536 rounds to 2.54. Now it gets a little bit tricky when you're dealing with the 5 rule. It's not as easy as normal math. So let's take a look. 2.5351. We have a 3 here, and we have a 5 next to it. Again, the 3 is the third sig fig, so we want to run around to this number here. If you have a 5, by rule, you must look at the next digit. So I got to look at this 1. If that digit is a non-zero number, then you're going to round that number 3 up. Okay. I know typically in math, if it's a 5, you round up, but statistically, there's a different way of dealing with it with measurement. So 2.5351, round to 3 sig figs. 3 is the third sig fig, next to it's a 5. By rule, I have to look here. If that number in that slot is a non-zero number, then I'm going to round up. So the 3 changes to a 4. All right, let's take a look at the next one. Round this to 3 sig figs. Well, 2.52. All right. Next to the 2 is a 5. So again, by rule, I have to look at the next digit. If the next digit is a 0, and it is, I must go back and I must look at the number that I'm rounding. If it is even, then I leave it. And the rule is called the even leave 'em rule. And the even leave 'em rule just means that that 2, because it's even, will stay a 2. But you got to understand, this is a very low percentage that's going to show up because 3 things have to happen. Think about it. The number you're rounding has to be even. The number next to that number has to be a 5. And following the 5 has to be a 0. Okay? So it's very low percentage chance that it's going to show up. But the answer will be 2.52. Well, what if that number is odd? So I'm rounding to 3 sig figs. 3 is the third sig fig. Next to the 3 is a 5. By rule, I have to look at the next digit. The next digit is a 0. So if it's a 0, I have to go back and look at the number I'm rounding. If it is odd, then I round it up. Up here it was even, so I left it. Down here it's odd, so I round up. So 2.5350 rounds to 2.54. The same thing would happen if you ended up with something like 2.52. And there was nothing after the 5, you have to assume that that's a 0. So if I was rounding this to 3 sig figs, the 2 is even. Next to it's a 5. I have to look at the next digit. There's nothing there, so we assume it's a 0. And that means that this is even, so this would stay 2. It would be 2.52. Another thing, 0 is an even number. So if we had 2.505, and we were rounding this to 3 sig figs, 2.5050. The 0 is even, next to it's a 5, followed by a 0. So I have to go look at this number, and that number is even, so this would round to 2.50. Alright, the last one is a sig fig, a scientific notation number, and we look at this value here, 2.53 times 10 to the negative 23rd. How many sig figs are here? 1, 2, 3. Remember that this would all be considered place value. So if we're rounding this number to 3 sig figs, it's already 3 sig figs. So it's going to be 2.53 times 10 to the negative 23rd. It's not going to change at all. So keep that in mind when you're rounding. All right. For calculations, 2 different rules. Multiplying and dividing. You're going to look at all the values that you multiplied and divided, and you're going to find whichever one of those values has the least number of sig figs. Whichever one has the least number of sig figs, you're going to round your answer to that amount. For adding and subtracting, you're going to look at all the numbers you're adding or subtracting, and you're going to see how far past the decimal they go. Your answer can only go past the decimal whichever one of the numbers went the least places past. So it's 2 different rules. One deals with least number of sig figs, and one deals with places past the decimal. The thinking here is that your answer cannot be any more significant or precise or accurate than the numbers you use to get it. So let's take a look at some sample problems. All right, multiplication, 10.77 times 3.55. How many sig figs in this number? There's 3. How many sig figs in this number? There's 4. Remember the 0 rule for sandwiched zeros. So our unrounded answer is 38.2335. What do we need to round it to? Well, the multiplication rule says you look at the numbers you multiply and you figure out which one has the least amount. Well, which one of these has the least amount of sig figs? The 3.55 only has 3. What's the third sig fig over here? There's the first one, there's the second one, there's the third one. So I'm rounding to the third sig fig, which is the 2. What's next to the 2? A 3. I don't have to look at any of these values. All I need to do is look at this 3. This 3 is below 5, under 5, so the 2 remains a 2, and my rounded proper answer would be 38.2. By writing it this way and rounding it, I don't give the wrong impression about my data. If I saw this number and it was a rounded number, I would think there's a lot more precision than the numbers that was used to get it. Alright, how about adding? 3.25 plus 2.879 plus 213.6. Adding rule, look at the places past the decimal. This goes 2 places past. This goes 3 places past. This goes 1. By rule, my sum cannot be more precise than the least precise number used to get it. Which one of these is the least precise? Well, this one only goes 1 place past the decimal. This goes 3, this goes 2. So my answer cannot go farther than 1 place past, which would be where? Well, that would be the 4. So my 4 is the 1 place past the decimal. What's next to the 4? A 2, that's below 5. So what does the 4 do? The 4 stays a 4. And my final answer is 220.4. Had I written this as 220.43, let's say I rounded to 2 places past, what I'm telling the readers is that my value here, that I got 2 places past, the numbers that I used to get it, at least all of them were 2 places past, and that's not the case. This only goes 1 place past. So it's basically scientists keeping up with proper exchange of data. All right, how about down here? We have a division problem. 5.34 times 10 to the 23rd divided by 2.129 times 10 to the negative 12. This is a division problem. It has the same rule as multiplication problem, which is look at the numbers you divided, figure out which one has the least number of sig figs. Again, multiplying and dividing has nothing to do with places past the decimal. It has to do with least number of sig figs. How many sig figs in this number? 1, 2, 3. How many sig figs in this number? 1, 2, 3, 4. So by rule, I go with the number that has the least amount, which would be this one, and that's 3 sig figs. Which one of these numbers is the third sig fig? Well, it looks to me like it would be the 0. What's next to the 0? An 8. The 8 is greater than 5, so the 0 would go to a 1, and I would round this to 2.51 times 10 to the 35th. Again, you're going to have to drag all this place value with you. You can't just write 2.51. The times 10 to the 35th is a big part of the place value for this number. All right, down here we have another addition problem. Again, with addition, all we're looking at is places past the decimal. 24.654 goes 3 places past. 15 doesn't go any places past. So my answer that I get cannot be more precise than the least precise of these two numbers. This number doesn't go any places past. So I must repeat that when I round. So which one of these would be the 1's position? Well, that would be the 9. Anything past the decimal, I'm misleading anybody looking at my data. So how do I round 39.654 to the 1's position? Well, what's next to the 9? A 6. So it's greater than 5. Again, I don't look at this stuff down here, just look at the 6. It's greater than 5, so the 9 changes to a 10, which of course changes the place value to 4. Now remember, when it changes to 4, the 4 has to stay in the 10's position, so I have to throw in a 0. And it's very important that I put that decimal, because if I don't, if I write the answer as 40, well, I'm basically saying that my precision goes to there. But we see here that the number that was in the 1 slot is a significant number because it's not a 0. So I have to take the significance all the way here. If I wrote this, that's just 1 sig fig. When I put the decimal there, I make that 0 significant. I could also write that and mean the same thing. So those are rules on adding and subtracting significant figures and rounding.